Hey everyone, welcome back, and today we're going to talk about gambler's ruin, which is a common problem in both statistics and game theory. So in this video, we're going to first cover the basics, for example, what is gambler's ruin, and derive some common equations we need. Then we're going to work on some sample problems related to gambler's ruin, and then we're going to work on deriving the stopping time, which is how long it takes for a gambler's ruin game to finish. And finally, we're going to apply gambler's ruin to a more difficult interview problem to see how we can use the equations we derived in this video to solve a difficult problem. So with that all that said, let's actually get started on what is gambler's ruin. So a common way of representing gambler's ruin is where we have a person, and this person has I dollars at the start. So the goal of this person is to earn his way all the way up to N dollars. And the way we do that is we bet $1 at a time on the outcome of a specific game. So for example, we could bet on the outcome of a flip of a coin, which has a half chance of winning, or we can bet on the outcome of a dice roll, which has a 1 in 6 chance of winning. So there's different chances of winning, but every time we're going to bet $1 at a time. So this is the key to gambler's ruin. So if we win this bet, then we're going to have, let's say we win, then we have $I plus 1, or alternatively, we could also lose. Then we're going to have $I minus 1. So if we keep winning, we're eventually going to reach N dollars, in which case we can leave the casino and we have 1, or we can keep losing all the way until we have $0, in which case we also end the game. So usually in this outcome, we call this the winning outcome, and we call this the losing outcome. So now we can quickly derive a equation for gambler's ruin for the chance of winning. So we want to know what is the chance of winning or reaching N dollars, supposing we start with a fortune of I dollars. So let's call that P of I. So P of I represents the chance of winning. Suppose we start with I dollars and the chance we actually eventually reach N dollars. So the alternative, P of I hat, is going to be the chance of reaching $0 starting from I dollars. So we don't know the chance of us winning each game, so let's call that R. So let's let R equals to the win rate of each game. And this is going to be independent for all games. So past games will not affect the win rate of future games. So now we want to look for a way to derive P of I. So what's the chance of us winning, supposing we start with I dollars? So at P of I, there's two outcomes. So let's say P equals to probability of winning a game, and let's let Q equals to 1 minus P, so the probability of us losing a game. So P of I is going to equal to P, lowercase p, times Pi plus 1. So if we won this game, then we're going to have I plus $1, and little p is the chance that we actually won this game. So alternatively, we could also lose this game, so it's going to be Q times P of I minus 1. So here, this is the win, and here, this is the loss. So we can quickly see that this is a recursive relation, as in P of I is dependent on P of I plus 1 and also P of I minus 1. But we don't actually want a recursive relation. We want something that we can actually solve and get a number for. So to do that, we're going to have to move some of the elements around. Let's actually move this equation down a little bit. So we know that P of I is the same as P plus Q times P of I, since P plus Q equals 1, since we either win the game or lose the game. So we can factor out these elements here. So we can have P times P of I plus Q times P of I. And this is equal to P times P of I plus 1 plus Q times P of I minus 1. So now let's move all the P's on one side and all the Q's on another side. And that's going to get us Q times P of I minus P of I minus 1. This is equal to P times P of I plus 1 minus P of I. So we can also move this Q over, this P over, so it's going to be Q over P times this thing. So this is one of the first equations that we're going to get, and this equation is going to be very helpful for us to derive an actual value for P of I. Since we don't want this recursive relation, we want a actual value. So now we have this, and we can actually test some numbers. So there's certain p's that we know for sure. For example, p of 0, this is going to be 0 because the chance of winning for us at $0 is going to be 0 since we lose the game at $0. Another one that we know is going to p of n. P of n is going to be 1 since we're guaranteed to win, because to define winning, we have reached n dollars, and p of n already reached n dollars. So that means we have a 100% chance of winning. So this is really important to keep in mind. So p of 0 is going to be 0, and p of n is going to be 1. So now we have this equation right here, and we can plug in some values for I. So let's say I is 1. What happens if I is 1? Then we have q over p, and let's move everything to the other side. So p of 1 minus p of, switching the sides is going to p of 2 minus p of 1. This is going to be q over p times p of 1 minus p of I minus 1, which is 0. P of 0. We know that p of 0 is 0, so we can just get rid of this term here. And now we got p of 2 minus p of 1. This is going to be equal to q over p times p of 1. So let's plug in another value. So this here is I equals to 1. We can also try I equals to 2. So p of 3 minus p of 2, this is equal to q over p times p of 2 minus p of 1. So notice that this p of 2 minus p of 1 here is the same as this p of 2 minus p of 1 here. So we can substitute that in. So we got p of 3 minus p of 2. This is actually equal to q over p in brackets squared times p of 1. So if we keep doing this, for example, we do p of 4 minus p of 3, we're going to notice that this is going to be q over p to the power of 3 times p of 1. And you can try this for some more numbers. We're going to notice the same pattern right here. So to put this into an equation, we can say that p of I plus 1 minus p of I, this is going to be equal to q over p to the power of I times p of 1. So this is the second really important equation that we got here. So this equation is going to really help us figure out what p of I actually is in terms of a value. So using this equation, notice that this here, let's do that in red. So this is the difference of consecutive terms. So I like to call it the difference of consecutive terms because if we add up all the differences of consecutive terms, lots of terms will cancel out. So this is the pattern we'll see. For example, we have p of I plus 1 minus p of I. This is the first term. Then we have p of I minus p of I minus 1. And then we have p of I minus 1 minus p of I minus 2. So on and so forth, all the way until we have p of 2 minus p of 1. So notice that here, this p of I and this p of I will cancel out. This p of I minus 1 and this p of I minus 1 will cancel out. So we can do a bunch of these cancellations all the way until we only have the first term and the last term. So what this is equal to is p of I plus 1 minus p of 1. So all this adding up the differences of consecutive terms is going to get us p of I plus 1 minus p of 1. But for each of these terms, we actually know what it is. For example, p of I plus 1 minus p of I, this is going to be equal to q over p to the power of I times p of 1, right? So this term here, this is going to be q over p to the power of I minus 1 times p of 1. So all of these are the same, and if we add all of these up, we're going to get what's called a geometric sequence. So this difference of consecutive terms is going to get us a sum of a geometric sequence, which is going to be p of I plus 1, minus p of I, starting with k equals to 1, ending with all the way at I. And this is going to be the same thing as q over p to the power of I times p of 1. Same thing, k equals to 1 all the way to I. So now we got something that's very interesting. So we got this thing here and this thing here, these two are equal. So we can move the p of 1 to the other side, so p of I plus 1, this is equal to the summation for q over p q over p to the power of I times p of 1 plus p of 1, starting with k equals 1 all the way to I. And we know that if I is equal to 0, so for example, this exponent here is equal to 0, then q over p to the power of 0 is going to be 1. So we can start k instead at 0 instead of 1, and then just remove this p of 1 element. So this is exactly the same thing here. So now this is a really valuable equation because this is no longer recursive. P of I plus 1 is only dependent on P1 and I. It doesn't depend on Pi plus 1 or Pi minus 1. So we're one step closer to actually deriving a value for P of I. So now we need to sum up this geometric sequence, and the formula for summing up the geometric sequence is right here. So it's going to be a r to the n plus 1 minus 1 all over r minus 1. So this is the formula here, where r, in our case, is going to be r equals to q over p. This is the common difference, or the common factor, sorry. And a is going to be the first term, since k is equal to 0 in the first term, and we can, let's factor out p of 1. So don't worry about p of 1 for now. That means the first term here is going to be a is equal to 1. So now we have two different cases. We have one case where p equals to q, so r is equal to 1, and we have a different case where r is not equal to 1. So we can't actually plug, so suppose r is not equal to 1 first, so we have a different scenario. Then the sum of this geometric formula is going to be q over p I plus 1 minus 1 all over q over p minus 1 if r is not equal to 1. So this is really ugly, but alternatively, if r is equal to 1, so q over p is equal to 1, that means the summation here is going to be just a bunch of 1s times p of I all the way until I, from 0 to I. So there's going to be I plus 1 elements. With I plus 1 elements, and they're all multiplied by p1, so this is going to be I plus 1. So now we have the two different cases. Let's call this case 1. Oops. And case 1 is where r equals to 1. So we know that p of I plus 1 is equal to p of 1 I plus 1. So this is from this thing right here. And what we know from that is that p of n is equal to p of 1 times n. Remember that we defined p of n to be equal to 1. So what that means is that 1 equals to p1 times n. So p1 equals to 1 over n. This is a very nice fraction here. Which means that, bringing it back here, p, let's say pj is a different term, is going to just be equal to 1 over n times j. Nice. So in this case, we're able to derive something that is not, for pj, that is not dependent on any of pj minus 1 or pj plus 1. We actually got a value here. And now we have to also look at case 2. So case 2, this is a lot uglier. So r is not equal to 1, or p is not equal to q. So what happens in case 2? We know that pi plus 1 equals to p1 multiplied by this big fraction here, so q over p to the I plus 1 minus 1 all over q over p minus 1. So now let's let I equal to n minus 1. So this means that p of n equals to p of 1 times q over p to the n minus 1 all over q over p minus 1. So now this is p of n. So moving p1 to the other side, we're going to get p1 equals to pn. So q over p minus 1 all over, we know that pn is equal to 1, so this is 1. So p1 is equal to q over p minus 1 all over q over p to the n minus 1. Sorry, my writing is getting really ugly here. And now we can bring this term to here. So finally, we're going to get pi, let's call that j now, instead of I plus 1, Pj is going to be equal to Q over P minus 1 divided by Q over P to the power of n minus 1 multiplied by Q over P I plus 1 minus 1. Oh, sorry, I plus 1 is J, so it's like that, over Q over P plus minus 1. So this numerator and this denominator will be able to cancel out. So we're going to get Pj is going to equal to, finally, a not super bad fraction, which is Q over P to the power of I minus 1, sorry, to the power of J minus 1 all over Q over P to the power of n minus 1. So this is the case where we have r not equal to 1, and we get P of j, which is equal to this really ugly fraction right here, based on Q, P, N, and J. So cool. So these are the two fundamental equations. Let me highlight them real quick. So this is probably the equation that we're going to see most often, since most of the time, Gambler's Rune will have a 50-50 chance of winning and losing. So if it's not a 50-50 chance of winning and losing, then we're going to have to plug in P of j, which is going to be this right here. So based on what the question asks you, we're going to be able to plug in one of these two equations to be able to find the probability of us winning the game. Nice. So after that out of the way, we can look at a sample problem. So a common sample problem is, instead of having one person play casino, we can also have two players play each other. So let's say we have person A, they have $3, and person B, they have $5. So they're going to gamble $1 at a time on a fair coin. So they're going to gamble $1 at a time, and they're going to gamble it on a fair coin. So on a fair coin until someone is broke. So until someone reaches exactly $0. So now this looks a little bit different to the Gambler's Rune problem we talked about earlier, where we're playing a casino. But instead of looking at it from A and B's perspective at the same time, we could just look at it from A's perspective. So we can look at the amount of money. So first of all, we could have $0. Let's draw it in a different color. So this is losing if we have $0, but we could also have, this is $1, this is $2, this is $3. So we're here right now. And we can also go all the way up to $8. So 4, 5, 6, 7, 8. And here this is winning. So any of the big thick blue lines is going to be us finishing the game. If we finish at a loss, then we're at $0. If we finish at a win, then we have $8. So what is the probability of A winning the game? So P, A winning. By A winning, that means that B is broke or A has all $8. So we know from the equation before that Pj equals to, let's actually write this in blue here. So Pj, this is equal to 1 over n times j. This is for if r is equal to 1. In this case, r is equal to 1 because we're playing a fair coin. So P and Q are both 1 over 2. So 1 over 2 over 1 over 2 is going to be 1. So that means we can actually use this equation here. So P of 3 is the amount of money we start with. This is going to be 1 over n, which is the total amount of money. The total amount of money here is going to be 8. So 1 over 8 times j, which is equal to 3. So this is going to be 3 over 8. So A has a 3/8 chance of winning, which is not too bad because he started with less money than B did. So alternatively, let's say they're not playing on a fair coin. Instead, let's say P equals to 0.3 and Q equals to 0.7. So the chance A wins on a single game is going to be 0.3, and the chance B wins on a single game is going to be 0.7. So now we're slightly unfavored. What is the chance of us winning this game? So now we have to use the other equation. Instead of this nice P of j equals 1 over n times j, we're going to have to use this one right here, which is going to be P of 3. This is equal to 7 over 3. So 7 because it's Q over P. Let's actually write this. Q over P to the power of j minus 1 all over Q over P to the power of n minus 1. So what this is equal to is going to be Q is 0.7, P is 0.3, so Q over P is 7/3. So 7/3 over J, which is equal to 3, all over 7/3 to the power of n, which is going to be 8. Both of these are minus 1. I calculated this previously, and this is roughly equal to 0.0133. So you might think this is actually very low, and it is, because we have a lower than 50% chance of winning each game, and we have less money to start with. So, but is this value too low? We can also look at the chance of us winning 5 games immediately. So the chance of us winning 5 games immediately to immediately win the game is going to be 0.3 to the power of 5, and this is equal to 0.00243. So this is a lot lower. Of course, we don't have to win all 5 games immediately. We can lose 1 and then win some, lose 2 and then win some. So the chance of us winning the game being at 0.1 or about 1% is roughly right. And it makes sense compared to the chance of us winning 5 games immediately. Hopefully you guys were able to learn something, and I'll see you in the next video.